So hello everyone and welcome to our YouTube channel. Today we have covered the topic of graph, a data structure. Graphs are fundamental concept in computer science and have a wide range of applications in various fields. They are powerful tools for representing and analyzing relationship between different entities. In this video, we will be explore the definition and purpose of graph, their component including nodes and edges, different types of graphs, and various ways to basically represent them. So, covering this agenda for traversing the graph, we have a DFS and BFS algorithm. The shortest path algorithms as a Dijkastra algorithm. For minimum spanning tree, we have to find it using Prim's and Kruskal's algorithm. And last but not least, graphs algorithm and applications. Introduction of the graph. A graph is a data structure consisting of nodes or vertices connected by edges. Nodes represented entities and edges represented connections or relationships between the nodes. Connections can be directed or undirected, indicating one way or two way relationships. Edges can be weighted to represent strength, distance, or a cost. Graphs are versatile and used to model real world scenarios like social networks and transportation networks, etc. They provide a flexible and intuitive way to analyze interconnected data. We have a definition of graph as a graph is a mathematical representation of node or vertices and the connections or edges between them. Graphs are defined as ordered pair of V, E, where V represent a set of vertices or set of nodes and E represented the set of edges or the set of connections between the vertices or nodes. Vertices can be labeled or unlabeled depending on the conditions. Edges can be directed or undirected, indicating one way or bidirectional relationships. Edges can have weights or values associated with them to represent metrics, cost, or distances. Graphs can be finite or infinite depending on the number of vertices as well as the number of edges. Graphs are extensively studied and utilized in fields such as computer science, mathematics, etc. They are valuable for modeling and analyzing complex relationships and systems. We have to cover the nodes and edges terminology. So for nodes, they are also known as vertices. They are the fundamental unit of graph. They represent entities, objects, or elements within the graph. Nodes can have the labels or additional information associated with them. For the edges or vertex, for the edges or connections, they are the connections or the links between nodes in a graph. They represent the relationships, interactions, or dependencies between the connected nodes. Edges can be directed, indicating a specific direction from one node to another, or undirected, signifying a bidirectional relationship. Weighted edges can be assigned values or weights to represent metrics, cost, or distance associated with the relationships. So there are types of graph: the directed graph and undirected graph. As given in the figure, the undirected graph, we don't know the direction where the node will travels. So it is undirected. For the directed, we have known the specific sequence of nodes. So in a directed graph, which is also known as digraph or edges, have a specific direction from one node to the another. The relationship or the edges between the node is asymmetrical, indicating a one-way connection. In undirected graph, the edges have no specific direction, so it indicates the bidirectional connection. We have weighted and unweighted graph. For the weighted graph, we can have each edge is assigned to a numerical value. Okay, it may be a metric, it may be cost, it may be distance, or any other relevant information associated with the relationship between the nodes. So by the weighted graph, we can show the relationship between the two nodes. In the unweighted graph, all the edges have the same value or the weight. There is no additional information or distinction among the edges based on their relationships. We can represent a graph by two ways, using adjacency matrix and using adjacency list. So by adjacency matrix, the adjacency matrix is a square matrix representation of a graph. Rows and columns of the matrix represent nodes and matrix entries indicates the presence or absence of edge between the nodes. So simply take this example 0, 1, 2, 3, 4, 5. For the element 0, we have connected 1, 2, 3, and 4. So for from 0 and 1, from row 0 and column 1, we have 1. Row 0, column 2, we have 1. Row 0, column 3, we have 1. Row 0, column 4, we have 1. But 0 is not directly connected with 5. So we have row 0, column 5, 0. Okay. Similarly, 1 is connected to 0 and 3 only. So row 1 and column 0 is 1. Row 1 and column 3 is 1. Rest all of are 0. Similarly, we have 4. 4 connected to only 0 and 2. So row 4, column 0 is 1. Row 4, column 2 is 1. Rest all are 0. This is the representation of graph in adjacency matrix. So just read this. If there is an any edge between nodes I and j, the matrix entry at position I comma j or j comma I is marked as 1. Otherwise, it is marked as 0. But in the adjacency matrix, if this is the directional graph, so this is I comma j and j comma I is not suitable. Okay. The second representation of graph is adjacency list. The adjacency list is a collection of linked lists or arrays used to represent a graph. Each node in a graph maintains a list or array that stores its neighboring nodes or the nodes it is connected. Okay. So A is connected to B and A is connected to C only. Okay. B is connected to E only. B is not connected to A. Okay. As it is the directed graph. C is connected to D only. From C we can go only to D. From D we can only go to B and E. From E we never go to any node. Okay. So this is the representation of adjacency list. Now talking about the implementation of graph in Python. So this is the code we have. A graph class which has a init self method with vertices. We have a method called add vertex, add edge, and get neighbors. In the add vertex, we have self dot vertices. If vertex is not in there, then add that. Okay. We have add underscore edge method. In this, we have vertex 1 and vertex 2. So we can add the edge between vertex and vertex 2 passing arguments. We have a get underscore neighbor method also. So we have one argument vertex. So for that vertex we have, if we pass any vertex to get underscore neighbor, we will get the neighboring vertex of them. Okay. Create an instance of a graph equal to graph class, add vertex abcd, add edges to connect the vertex a b b c c d and e. Neighbors are graph dot get neighbors of b. What are the neighbors of B? This is the question. You can do it by yourself. But for now, B is connected to C. Okay. A is also connected to B. Apart from that, D is not connected to B directly. Okay. So neighbors of B are A and C. So you will get this output. So the graph class is created with an empty dictionary vertices as an attribute. The add underscore vertex method add a vertex to a graph by adding an entry to the vertices dictionary. The add underscore age method connects two vertices by appending each vertex to the other's list of neighbors. The get underscore neighbors method returns the list of neighbors for a given vertices. And here is the example. You can try it by yourself. Now we come to traversing the graphs, that is DFS and BFS. In the depth first search, we have DFS is an algorithm used to traverse a graph. It explores the graph by going as deep as possible before backtracking. The algorithm starts at a chosen node and explores its neighbors recursively. It continues to explore the unvisited neighbors until reaching a node with no unvisited neighbors. Then backtrack to the previous node and explores other unvisited neighbors. That's how the DFS works. For the BFS, breadth first search is an algorithm used to traverse a graph. It explores the graph level by level, visiting all the neighbors of a node before moving to the next level. The algorithm starts at a chosen node and explores its neighbors first. It then visits the neighbors of the visited nodes, ensuring all the nodes at the current level are visited before moving to the next level. Now we have a shortest path algorithm, Dijkastra algorithm. We have a Dijkastra algorithm which is used to find the shortest path between two nodes in a graph. It works for graphs with non-negative edge weights. The algorithm maintains a priority queue of nodes, prioritizing the ones with the shortest known distance. It starts from a source node and iteratively explores the neighboring nodes, updating the distance to each node if a shorter path is found. And here are the steps given for the process to find the shortest path. Initialize the algorithm with the source node and set its distance to 0. It select the nodes with the smallest distance from the priority queue. For each neighboring node, calculate the distance through the current node and update it if shorter. Mark the current node as visited. Okay. We have to repeat this 2 to 4 until all the nodes have been visited or the destination node is reached. Okay. Another important concept is minimum spanning tree. We can find the minimum spanning tree using Prim's and Kruskal's algorithm. We will see in the next slides. So minimum spanning tree. A minimum spanning tree is a subgraph of a graph that connects all the vertices with the minimum total age width. It does not contain any cycles and includes all the vertices of original graphs. Finding an MST is useful for various applications such as network design, clustering, and optimizing resource allocation. So it is the important point. It does not contain any cycles, so we need to remove any cycles if it happens. To work with the Prim's algorithm is used to find the minimum spanning tree of a connected weighted graph. The algorithm starts with an arbitrary vertex and gradually grows the MST by selecting the age with the minimum weight, connecting the current MST to a new vertex basically. So if we connect if we have a node selected as 1, so from 1 we can go to 6 or 2. So we have gone to 6 because its weight is 10 less than 28. After that we need to go to 5. After that we can go to 7 as well as 4, but as 22 is less we will go to 5 to 4. Okay, from 4 we can go to 7 as well as 3, but 12 is less than 18, so we go to 3. After 3 we go to 2, which is 16, and after 2 we go to 27. It uses priority queue to keep the track of the minimum weight ages. The next algorithm is Kruskal's. So basically, Kruskal's algorithm is another approach to find the minimum spanning tree of a connected and weighted graph. The algorithm starts by sorting all the edges in non-decreasing order of their weights. It iteratively selects the edges with the smallest weights and add them to the MST if they do not form a cycle with the already selected edges. Okay, so here cycle do not form a cycle is a very important point. You can see in this graph, if we can select a one first stage, then we can select a third edge, and then we can select second edge. Then we have to select a fifth edge. Why fifth edge? 1, 5, 3, and 2. These are the selected edges for Kruskal's algorithm by Kruskal's algorithm. So it works on the edges. Okay. So the algorithm uses the concept of disjoint sets to efficiently detect the cycles. Now moving further, graphs, algorithms, and applications. So we have a network analysis. Graph algorithm plays a crucial role in network analysis where they are used to analyze and understand complex networks. These algorithms are applied in various domains, including social networks, transportation networks, communication networks, and many more. Graphs analysis provides insights into network structure, connectivity, shortest path, flow optimization, and other important metrics. For social networks, the graph algorithms are ex- extensively used in social network analysis to gain insights into relationships and patterns within the social networks. Applications includes community detection, which identifies groups of closely connected individuals. Centrality measures that determine the importance of nodes, recommendation systems for suggesting connections, and influence analysis to identify the influential individuals or trends. We can move towards use cases and applications. Routing and navigating. The graphs are widely used in routing algorithms to find an optimal path. Social networking and recommendation systems, the graph plays a crucial role in it. Network and infrastructure analysis, the graph are used to analyze the network structure, identify the bottlenecks, and optimize the infrastructure. For the application, we have BFS and DFS as breadth first search and depth first search for pathfinding algorithms. Social network analysis, we have a group algorithms enables the analysis of social networks, identify the influential nodes, detecting communities, and studying social dynamics. For network analysis in biology, we have graph theory finds applications in modeling biological networks such as protein interactions, gene regulatory networks, and metabolic pathways. These are a few applications and use cases of graphs. In conclusion, the graph data structure is a powerful tool for representing and analyzing the relationships between the entities. With its nodes and edges, graphs provides a flexible and intuitive way to model complex systems and solve various problems from directed and undirected graphs to weighted and unweighted graphs. There are different types of to suit different scenarios. The adjacency matrix and adjacency list are common representation used to store the graph data. Python usually offers convenient ways to implement graphs, allowing the creation of a graph class, adding vertices and edges, and performing traversal using algorithm like DFS and BFS. Graphs algorithm such as Dijkstra's algorithm for finding the shortest path, as well as Prim's and Kruskal's algorithm for minimum spanning tree, further enhance the versatility of graph data structures. Basically, graph finds applications in network analysis, social networks, biology, and routing and navigating, recommender system, and many more. They enable efficient connectivity, analysis, insight generations, and optimization in various domains. While graphs have advantages like flexible representation and efficient connectivity analysis, they also come with challenges with memory and processing, overhead, and complexity. So that's it for this video. Thank you for watching. We will see you in the next. Bye.